Hello students, welcome back. We are done with section 1. Let's go to section 2, Systems of Linear Equations. Let's see how it is related to matrices. Here are some examples of systems of linear equations. Homogeneous versus non-homogeneous. The right-hand side is all 0, no constant. That's homogeneous. And not everything is 0, that's non-homogeneous. A little bit more general case. And please note that these systems of linear equations can be simplified into this matrix multiplication form. Let's check. First row, first column. So a11 times x1 plus a12 times x2 plus a13 times x3 plus and so on. In the end, a1n times xn. Add them all up. That's the left-hand side. Okay. And the right-hand side, of course, is C1. So from this matrix multiplication, the first row gave me the first equation. Repeat the same thing to the second row. You're going to get the second equation. And repeat until the end. The last row, the mth row times this column will give me the mth equation. So what does that mean? This system of linear equation and this matrix expression are the same. And naming this matrix as A, this as X, and that as C, we can write this entire system in a single line like this. A times X is equal to C. And for homogeneous case, instead of C, we are going to get 0. Basically, it's this. A times X is equal to 0, or A times X is equal to C. Here, I specify the sizes of those matrices. M by n matrix times n by 1 matrix is equal to m by 1 matrix. Now, m by n matrix, if this is usual, the general rectangular matrix, that means I have m equations and n unknowns. Will that work? Say 3 equations and 5 unknowns. Will that work? Or 5 equations and 2 unknowns. Will that work? Use your common sense. They're not going to work. So we're going to work primarily upon the square matrices, n by n matrices, which will give me n equations and n unknowns. Well, there's a nice theorem here. If there are more unknowns than number of equations, then the system of linear equations cannot have unique solution. The solutions are not unique, so there are more than one solutions. Consequently, there are infinitely many. And this theorem is actually really significant and really hard to prove. And I just copied and pasted from linear algebra notebook, and then I'm just opening these cells to make you realize what kind of depth this problem has. And that's about it. Just look at the shear length. So of course we are not going to do it. We're just going to take it for granted and just use this result. So if the number of unknowns is more than the number of equations, then no good. Non-unique solutions. And what if number of equation is more than number of unknowns? That too is going to be a problem too. But that's actually a little bit easier, and it comes from the corollary from here. But Now, this is not a linear algebra class, so I'm not going to go into really significant theorems with difficult proofs. Just take my word for it. In order to have anything that resembles a chance that you can work things out, we have to have n by n, so that n equations and n unknowns, and thus we are dealing with square matrices. So we can bring these down like this. Now no more n by n. I brought it down to n by n. N by n. Did you notice? How did I reduce from n by n to n by n? Actually, they come from very significant theorem from linear algebra. Let's not go into that. Just use common sense. We need n equation for n unknowns. That's why we need those. And once we have those square matrices, now things are a little bit easier from this point on. In order to have a unique solution, if I have a times x is equal to c, and if a is invertible, then I can multiply a inverse to both left-hand side and right-hand side. Yes, because we started from the equality here, I can do the same thing to both numerator and denominator, both left-hand side and right-hand side. I decided to multiply the same thing to left-hand side and right-hand side of the equality. Now, what is A inverse times A? It's identity matrix. That's the definition of the inverse matrix. Remember, that matrix times original matrix is identity. How about this X inverse? Oh, sorry about the typo. A inverse times C. Well, this is an n by n matrix, and this is a column vector, so the result will be column vector, which I'm going to name as X star, because C is specific constant. So A inverse times C2 is a constant, so I'm going to name it as X star. And what do I get? X is equal to X star. That's what I'm getting right, because I is identity, so I times something stays there. So what did I get? X is equal to X star. I ended up solving this equation, solving this system of linear equations using just matrix expressions. So we have a unique solution. Just one and only one solution. The other direction, well, I'll just leave it at those. We can do all those in linear algebra class, so let's move on. In short, we are looking for inverse matrices. Okay, alright. Now, there may be some students who are wondering, why in the world are we studying these systems of linear equations and inverse matrices? Why? Finally, here's the answer to that question. Let's use those to study systems of linear ordinary differential equations. Here's the general form of a system of linear ODE with constant coefficients. So we have the derivative functions, y1 prime, y2 prime, and so on. There are n functions, y1 through yn, so we have n derivatives, n first derivatives, they're all here. And the functions y1 through yn, n original functions, or zero derivatives. And then the right-hand side, k1 through kn. That's the traditional form, and if you use matrix expression, you can rewrite this thing like this. by prime plus cy is equal to k. Does it make sense? If it doesn't, let's open up. Now all these are b's, coefficient for these, and then these are y prime, so y1 prime, y2 prime, and so on. And all these are c's, this matrix here, and then we have y, y1, y2, y3, those kind of things. And if you take matrix multiplication, first row times first column, that's going to give me this. Second row times this column, that's going to give me this in the second line, and so on. Same goes here. First row times this column, it'll give me this part from the first equation. Second row times this column will give me this part from the second equation, and so on. And the right hand side is k1, k2, and so on. So yes, this expression where b is this, c is that, y and y prime are this and that, and k is like this, it makes perfect sense in matrix form, except that this is a lot simpler than those. Okay, alright. From the general form, we reduced like this, and let's reduce still further. Make it into standard form like this. Solve it for y prime. How do we do that? We can do it like this. From here, which is the first equation here, and then flip the cy to the other side by subtracting. No big deal there. Now from here, multiply b inverse to both left-hand side and the right-hand side of the equality. And then we'll have to distribute the multiplication. Oh well, never mind. Let's write like this. So from here, second equation, multiply b inverse to both left-hand side and right-hand side of the equality. And then the left-hand side, simplify. B inverse times b is identity matrix I. So that just disappears and I just have y prime. That was the idea. And to the right-hand side, I use distributivity. So minus of b inverse times c, and then b inverse times k. And if I name this as matrix A, and if I name this column vector as column vector function f, yes, this is n by n matrix, and this is a column vector. So yeah, we have column vector f. Then this whole thing, which started from this big thing, became that. Assuming that B, this matrix B is invertible. If it is not, then that means we don't have enough information about the derivatives, so this whole differential equation, this whole system of linear ODEs will not work, so you don't have to worry about that kind of circumstance. So anything in general can be reduced into the standard form if it's gonna work in the end, of course. And then that can be reduced into this kind of system. I didn't choose a good word. It's not a reduction. This is simpler, so from here to there is not a reduction. It's just that from here to that is a reduction. So from the general form, where those derivatives and the originals are all intertwined, into each line has just one derivatives. Just y1 prime equal to something, y2 prime equal to something, and so on. Yn prime is equal to something. This is an improvement. And of course, this one here, which I highlighted, is even bigger improvement. So what did I get? Using matrix expressions, you can work out a system of linear differential equations and use those standard forms, and then we can go from there. Already it is turning out that matrices are very, very useful for systems of linear EDEs already. Now let's go one step further. Let's consider some special system of linear ODEs, a homogeneous case. Let's see, previously, this was the general case, non-homogeneous case. We had this plus f. Let's suppose there's no such thing. Then we have homogeneous equation. And then let's consider a initial condition, y of 0 is y star. Then it is possible to rewrite it into this very strange form. Y of t is equals to e to the at power times y star, which makes a lot of sense if all these had been one-dimensional function. What am I talking about? Let's suppose we have this in one-dimensional case. Let's suppose we have something like this. It's an initial value problem. How would you handle that? Well, if you use separation of variable, you can actually get there. Let's see. We have enough time, so let me show you. It's equal to a times y, so we can write like that. And of course, I can put integrals to both left-hand side and right-hand side. So log of y is equal to a t plus some constant say k. Okay, all right. That's as good as any. So y is therefore exponential of a t plus k, and that can be written as exponential of a t times e to the k power. So y is some e to the a t times something. Let's say you can write like this, but it turns out if you plug in the initial condition t equal to 0, then t equal to 0, this will become 1, so this c will be the same as y. It will become like this. So for one-dimensional case, it makes perfect sense. But for matrices, does this make sense? That is a big question. We do not have separation of variables. We cannot divide like this. Certainly, this method will not work for matrices. But amazingly, it still works if you cleverly define this exponential, the matrix exponential. How do we do that? We use Taylor-Maclaurin expansion like this to define it. Now, look at this. This is typical Taylor-Maclaurin expansion of exponential function, except that this capital A is a matrix. And then look at this expression. We have repeated matrix multiplication, but matrix multiplication is well defined. These are all square matrices, n by n square matrix, and multiplying I, which is again n by n, it's identity matrix, and an A squared. I mean, all these are just well-defined multiplication, and T is scalar, so scalar multiplication. So this makes complete sense. So it's well-defined. Now, does this thing satisfy all the rules of derivatives associated with exponential function so that this is a solution? Yes, it is, and that's something we intend to establish. Okay, all right. So much for section 2. Thank you. Let's stop here.